So moving on to Chapter 4. Chapter 4 deals with three major classes of chemical reactions. And because these chemical reactions are solution reactions, we begin this chapter by kind of a qualitative analysis of solutions and thinking about solutions. So our first two sample problems will kind of deal with that. And because a lot of these reactions deal with the reaction of ions in solution, we'll talk about how we can represent aqueous ionic substances in equations, both molecular equations, what we call total ionic equations, and net ionic equations. So even though there's not a specific sample problem associated with this concept, it's kind of an integrated part of these three kinds of chemical reactions. The first kind is precipitation reactions, and basically what happens is you're mixing two solutions together, and based on the new pairings that you might have, you might generate something that's insoluble or generate a precipitate. So we need to understand how to use data that's presented in Table 4.1. Again, this is material that will be provided for you in Gen Chem 1. In Gen Chem 2, though, once we get into more detailed aspects of solubility, the expectation is that you know these solubility rules. But again, they'll be provided for you in Gen Chem 1. Second kind of reaction we deal with is acid-base reactions. And acid-base reactions are so important. We actually have several chapters in Gen Chem 2 that are devoted to it. So we're just introducing the concept right now. We're introducing the concepts of titrations, and you'll do some titrations in the laboratory component of the course. But we'll also deal with some calculations here, and we'll have a sample problem where we will use data from a titration to solve a problem. And then the last kind of problem that we deal with in this chapter is oxidation reduction reactions, or what we call redox reactions. So where we have electrons that are being traded back and forth between species. So whether you've heard of Leo Gur or oil rig, whatever it happens to be, we need to think about those kinds of chemistry. So we'll practice assignment of oxidation numbers and being able to look at reactions and tell if redox has happened, and if so, identify who's being reduced and who's being oxidized. So again, three tables are really important in this chapter. Table 4.1 is provided for you, that's solubility rules. Table 4.2 is not provided for you. It's expected that you will know kind of these strong acids and weak acids and bases here. And so we'll deal with that a little bit more when we do those problems. But also Table 4.3 is one that teaches us how to assign oxidation numbers. So again, this is kind of a strategy table, not one that's provided for you on the quiz or exam. All right. So what we're going to do is work through these first two problems here. These first two sample problems have to do with kind of qualitative aspects of solution chemistry. We introduced solution chemistry at the end of Chapter 3, but we're going to think about it with a little bit more detail here. And so I really like to work through problems that I call molecular scene problems, and that's because they show us scenes of molecules, and we have to use these visual cues to understand what's going on. So oftentimes we'll be counting particles, or we'll need to look at what's happening to kind of make some decisions about which of these might represent the actual molecular scene. And this first problem, excuse me, truly is that. So they tell us that the beakers contain aqueous solutions of the strong electrolyte potassium sulfate. So the first part says which beaker best represents this compounded solution. They don't show us waters, but they tell us that we have the strong electrolyte potassium sulfate. Well, the first thing that we need to make sure that we're comfortable with is reviewing again Chapter 2 and knowing that potassium is a monovalent cation, sulfate is a divalent anion. Monovalent, +1 charge, divalent, -2 charge, anion, cation. So what this means is this guy starts out in solution as K2SO4, but when it dissolves, and because it's an ionic compound, dissociates into solution, we're going to get 2 potassium cations for every 1 sulfate anion. So that's information that should be helpful for us to solve this part A here, which we have to figure out which one of these beakers really represents the solution that we have here. Well, if we look at beaker A, what we can see here is we do see a divalent anion and monovalent cations and present in the right ratio. So that's good. That's what we would see for potassium sulfate. But because they tell us it's a strong electrolyte, that means we should have these species broken apart as ions in solution, not still together as an insoluble ionic compound. So what we really have here is K2SO4 that really has not dissociated. Those ions are still staying together. So our solution is not A, because this does not depict a strong electrolyte. So this is not depicting a strong electrolyte. And the problem tells us that potassium sulfate is a strong electrolyte, and because that's a very soluble ionic compound, we should know that it's a strong electrolyte. All right, so let's look at B here. So if we take B, okay, in B we can see that we also have this divalent anion and monovalent cations, but it still has not fully dissociated. So we can also say it's not B because it is depicting what we'd call a weak electrolyte. So A is truly depicting a non-electrolyte, and B is really representing what we refer to as a weak electrolyte, something that partially dissociates. So it's not B either. All right, spoiler alert, it's C, but let's look at D and explain why it's not D. Okay, so D, if we take D here, D finally shows us a strong electrolyte. So this shows a strong electrolyte, which is a positive thing, right? That's what we'd expect. But look what we see here. We see 1, 2, 3, 4, 5, 6 divalent anions and 3 monovalent cations. We see the anion to cation ratio, ratio as 6 to 3, right? Or a 2-to-1 ratio of anion to cation. That's not what we'd expect to see based on the molecular or the chemical formula for potassium sulfate. We'd expect to see twice as many cations as we do anions. So because of that, it's not D. Even though it shows a strong electrolyte, it shows a cation to anion ratio of 1 to 2, where we'd expect it to be 2 to 1. All right, so it is C. Yes, our solution for potassium sulfate is C. We see a strong electrolyte. The ions have completely dissociated. And then we see the correct cation to anion ratio of 2 to 1 there. Okay, so that answers part A. Beaker C is our correct beaker. To answer part B, we need to do something that's very common in molecular scenes problems, which is basically physically counting the spheres that we see. So it tells us each particle represents 0.1 mole. What's the total number of particles in solution? So if we count these here, we're going to see that there's 6 K pluses and 3 SO4 2 minuses. So basically that represents 9 particles. Okay, if each particle, so at 0.1 mole per particle, means that we have 0.9 mole of ions. So hopefully that makes sense to everybody. Each particle represents 0.1 moles. We have 9 particles, so that represents 0.9 moles of ions. The question asks us, what's the total number of particles? And anytime you see particles, whether it's ions, molecules, atoms, an individual particle, we need to use Avogadro's number. Okay, so Avogadro's number here is going to tell us that 1 mole of ions is 6.022 times 10 to the 23rd particles. Right, 1 mole of ions is that many particles. Math here gives us then 5.42 times 10 to the 23rd particles. And again, these particles are ions. So we'd have that many ions in solution.